Hi, my name is Marcelo Zimmer. I'm a weed science program specialist at Purdue University, and today I'll be talking about the antagonism of ACCase inhibitor herbicides that can be used in Xtend soybean systems for the control of volunteer corn. Volunteer corn is one of the most important weeds in soybean systems in Indiana. It is a weed that grows from corn grain that is left in the fields after corn harvest due to defective harvesting equipment or poor operation of the combines, as well as extreme weather such as hailstorms and high winds. The impact of volunteer corn and soybean systems include soybean yield losses, which will depend on the density and removal timing of the volunteer corn, but they can also serve as hosts for corn rootworm, and they can also cause harvesting issues depending on density and vegetative stage at the time of soybean harvest. The herbicide options that we have available for control of volunteer corn and soybeans will depend on the herbicide tolerance traits of the corn that was planted in the previous growing season. Corn hybrids such as non-GMO will be susceptible to both glyphosate, glufosinate, and the ACCase herbicides. Smart stack corn hybrids will be tolerant to both glyphosate and glufosinate herbicides. And enlist corn hybrids are going to be tolerant to both glyphosate, glufosinate, and the FOP chemical family within the ACCase mode of action. Several farmers grow smart stack corn hybrids which are resistant to both glyphosate and glufosinate herbicides, limiting the options for volunteer corn control to the ACCase herbicides such as the chemical family of the FOPs and the DIMs. Luckily, previous research indicates the high efficacy of both chemical families of graminicide families reported for the control of herbicide-tolerant volunteer corn. Previous research has indicated that several broadleaf herbicides can antagonize the efficacy of ACCase inhibitor herbicides on the control of grassy weeds and volunteer corn. Synthetic auxin herbicides such as 2,4-D and dicamba, as well as also glyphosate, are known to antagonize ACCase inhibitor herbicides for the control of glyphosate-resistant volunteer corn. And with the widespread adoption of Xtend soybeans for the management of herbicide-resistant weeds such as palmer amaranth and water hemp, we can expect the issues with the antagonism of ACCase herbicides to increase. We also have seen some industry research reports showing the reduced control of volunteer corn with Clethodim when that product is think mixed with dicamba or acetochlor. Therefore, we developed the hypothesis that the addition of dicamba plus glyphosate or acetochlor will reduce the efficacy of Clethodim and Quizalofop on the control of volunteer corn. We also hypothesized that the antagonistic effects of dicamba plus glyphosate and acetochlor can be overcome by increasing ACCase field use rates by 50%. That second part of the hypothesis was developed based on observations from the industry that were shared with us. Our specific objectives were to investigate the effect of dicamba and acetochlor on the efficacy of Clethodim plus Quizalofop when used for control of volunteer corn, and also to evaluate the effect of different ACCase field use rates when think mixed with dicamba plus acetochlor. To answer the questions posed by our hypothesis, we conducted field experiments in the 2020 growing season. We tested 3 different corn hybrids that were planted at 90,000 seeds per hectare across Xtend soybean plots. The 3 corn hybrids included a non-GMO corn trait, a smart stack corn hybrid, which is tolerant to both glyphosate and glufosinate, and also enlist corn hybrid, which is tolerant to both the FOP chemical family of the ACCase herbicides, as well as glyphosate and glufosinate. Due to time limitations, today I'm only going to be talking about the smart stack corn hybrid, which is tolerant to both glyphosate and glufosinate. Treatments in this experiment were arranged in a factorial design. Factor 1 was the ACCase herbicide active ingredient, which was either Quizalofop or Clethodim. Factor 2 was the ACCase herbicide use rate, which for Clethodim was either 70 or 105 grams of active ingredient to the hectare, which I will be calling the low and high rate from now on, which is equivalent to either 4 or 6 ounces of a Clethodim 2EC formulation, which was used in this experiment. For Quizalofop, we use either 31 or 46.3 grams of active ingredient, which I'll be calling the low and high rate from now on, of an assured 2 formulation, which is equivalent to either 4 or 6 ounces to the acre. Factor 3 was the addition of dicamba plus glyphosate at the specified label rates, and factor 4 was the addition of acetochlor at the specified label rate. We also added ammonium sulfate and crop oil concentrate to all the treatments without dicamba plus glyphosate, and we also added drift reducing agent and a non-ionic surfactant to all the treatments that had dicamba plus glyphosate as per label recommendation of Xtend. All the treatments in this experiment was sprayed with a TJET TTI 110-015 nozzles at 140 liters to the hectare. We used the same nozzle for all treatments to exclude the effect of nozzle types on the antagonistic effects of synthetic auxins to the ACCase herbicides. The volunteer corn height at application ranged between 20 to 48 centimeters, which is equivalent to a V5 to V6 growth stage. The data collected included visual control in a 0 to 100% scale at 7, 14, and 21 days after treatment. Today I'm only going to be showing data for 21 days after treatment. We also evaluated corn density and the number of corn ears at soybean harvest. The corn density and number of corn ears per meter square correlated very well. Pretty much every single corn plant that was alive at harvest was also producing a corn ear. We also submitted all the data to a factorial analysis of variance using Proglymics and SAS with mean separation using 2K HSD adjustment. Now let's move on to the results and discussion. Today I'm only going to be showing the data for the control of glyphosate and glufosinate tolerant corn. We ran a factorial analysis of variance for the control of glyphosate and glufosinate tolerant corn at 21 days after application, and we found a 4-way interaction with a p-value of 0.003. When we have a 4-way interaction, the best way to analyze the data and actually make any sense out of that data is to split a 4-way interaction into different 3-way interactions. Due to the occurrence of a 4-way interaction in this experiment, the data is divided by ACCase active ingredient. In this graph, we're showing the control with Clethodim tank mixtures for a glufosinate and glyphosate tolerant corn hybrid at 21 days after treatment. The tank mixtures with the low rate of Clethodim are on the left side of the graph, and the tank mixtures with the high rate of Clethodim are on the right side of the graph. The x-axis shows all the different herbicide treatments tested with Clethodim, and the y-axis shows the different control ratings ranging from 0 to 100%. The graph also includes the letters of significance for the Tukey analysis at the bottom of each one of the bar graphs. As we can clearly see, the addition of dicamba to Clethodim treatments reduced the control of the glyphosate and glufosinate tolerant corn. Also, the acetochlor appeared to reduce the control of Clethodim on the glyphosate and glufosinate tolerant corn. And when dicamba plus glyphosate and acetochlor and tank mix, we appear to have a 3-way interaction between those herbicides, resulting in the highest reduction of control for the glyphosate and glufosinate tolerant corn at 21 days after application. The figures in this slide just illustrate the results that we saw in the previous slide. Basically, the addition of dicamba plus glyphosate to either the low rate or the high rate of Clethodim can reduce Clethodim efficacy. However, the greatest reductions in control with Clethodim are seen when both dicamba plus glyphosate and acetochlor are added to the Clethodim treatments at both the low rate and the high rate. Now we're looking at the control of glyphosate and glufosinate tolerant corn at 21 days after treatment with the Quizalofop herbicide. The layout of the graph is similar to the previous graph that we saw a couple of slides ago. And basically the main message here for this slide is that whenever we added dicamba plus glyphosate to any of those Quizalofop treatments, we had a great reduction in the efficacy of this herbicide. Acetochlor does not appear to influence Quizalofop efficacy either in tank mix with dicamba or without dicamba. And these pictures here basically illustrate what the previous graph has already shown. Quizalofop at the low and high rate is antagonized by the addition of dicamba plus glyphosate. The addition of acetochlor to those treatments does not appear to influence the efficacy levels. We also evaluated the density of the glyphosate and glufosinate tolerant corn at the time of soybean harvest. In this graph here, we're showing the density only for the treatments that included dicamba on those tank mixtures for both Clethodim and Quizalofop products at the low and high rates. And basically what we can see is that the addition of dicamba, especially to the low rates of Quizalofop and Clethodim, resulted in the highest increases of volunteer corn density at the time of soybean harvest. And also we can see that the addition of acetochlor influences the efficacy of Clethodim, but it does not appear to influence the efficacy of Quizalofop. The conclusions of this experiment were that the addition of dicamba plus glyphosate to the post-applications of Clethodim or Quizalofop will reduce control of volunteer corn in Xtend soybean systems. Also, acetochlor will reduce Clethodim efficacy when tank mixed with dicamba plus glyphosate, but it did not reduce Clethodim efficacy by itself. Furthermore, the addition of acetochlor does not appear to reduce volunteer corn control with Quizalofop herbicide. Also, increasing the rate of ACCase herbicides by 50% resulted in increased efficacy, although many treatments still resulted in extending plants at the time of soybean harvest. The results of this study implicates that ACCase herbicide rates higher than the rates that we tested in this experiment would be necessary to overcome herbicide antagonism when tank mixing these herbicides with dicamba plus glyphosate, especially if acetochlor is added in the case of Clethodim. Also, split post applications and improved adjuvant use could be other alternatives for overcoming the antagonism of ACCase inhibiting herbicides with dicamba, although I haven't tested that on this particular experiment. For future research, some of the avenues that can be investigated are the physiological basis for the antagonism response of Clethodim to the addition of acetochlor plus dicamba. Also, assess the efficacy of ACCase herbicides with other group 15 residual herbicides such as S-metolachlor and peroxasulfone, and also to evaluate the effect of broadleaf herbicides labeled for enlist soybean systems in text mixtures of those ACCase herbicides as well, which is actually some of the research I'm presenting in my poster. With that, I'd like to acknowledge the Purdue Weed Science Lab for their help. These are the references I use in conducting this experiment. Thanks for watching, and I'll be happy to take any questions you might have.